Bismillahirrahmanirrahim. We continue our discussion on CPU scheduling and discuss furthermore CPU scheduling algorithms. But before proceeding ahead, you first have to recap the algorithms we have already discussed in previous lectures. In previous lectures, we discussed basic concepts related to CPU scheduling. Those were the concepts we had been discussing in previous chapters, such as what is CPU scheduler, what is the task that it performs, what is dispatcher, what task is being performed by dispatcher. Then we discussed scheduling criteria. 5 different criteria have been discussed and their optimization were also considered. We then started CPU scheduling algorithms. You can also call them as CPU scheduling policies. So 2 policies have been discussed in previous lectures. The first one was first come, first served, which was a non-preemptive policy. And in first come, first served, in whatever sequence processes arrive in RAM, in that very sequence CPU is assigned to them. It is a non-preemptive version in which if a long process has been assigned CPU, so operating system will not preempt it in the middle and take CPU away from it. Then we redefined first come first served algorithm, and as a result we got a new algorithm which was named as shortest job first. The shortest job first, as the name indicates, the priority should be given to those processes who have short CPU cycles. So the short process should be placed at the top of the ready queue, and the long process, those processes whose CPU cycle is long, should be placed at the tail of the CPU, at the tail of the ready queue. And in that order, CPU is then assigned to them. Shortest job first algorithm comes in 2 flavors. It has 2 versions or 2 variants: the non-preemptive version and a preemptive version. In non-preemptive version, the first ever process, whatever is its CPU length, once CPU is assigned to it, then CPU cannot be taken away from it or it cannot be preempted. While rest of the processes are arranged on the basis of the CPU cycle. So then the smallest will reside at the top of the ready queue, while the one which has come first is executing on CPU. So the smallest process will be residing at the top of the RAM and the largest will be residing at the bottom of the RAM. The next variant is the preemptive version of shortest job first. In preemptive version, no matter which process comes first, either small or large, once CPU is assigned to it and when some new process arrives in RAM, if its CPU time is smaller than the remaining CPU time of the currently executing process, so the currently executing process is then preempted and CPU is assigned to the newly arrived process. So this preemptive version of shortest job first is then given the name as shortest remaining time next, as we compare the times of 2 processes. The one which is executing, its remaining time is calculated and compared with the CPU time of the newly arrived process. So these were the 2 algorithms that we discussed, and we had seen that shortest job first is quite optimal as compared to the first come first served algorithm, and still the preemptive version of shortest job first is more optimal than its non-preemptive version. Now let's proceed with today's discussion. We'll see some more algorithms in today's discussion. What are more CPU scheduling policies or CPU scheduling algorithms? We now need to discuss them and see which one is better than the previous one discussed. So next scheduling algorithm is priority scheduling. As the name indicates, in this algorithm, some sort of priority has been given to processes. Now, priority can be on any basis. For example, shortest job first is also a priority algorithm in which the priority is given to processes which have short CPU cycles. Similarly, operating system can assign priority on some internal factors which are not known to the user. Now, if the specific priority scheduling algorithm is implemented, so in that case, a priority number, which is generally an integer number, is linked with every process. So for example, P is the process, P1 is the process, so priority number is assigned like this in parentheses. For example, its priority number is, this is the integer number that shows the priority of this process is 6th. So the CPU is allocated to the process with the highest priority. So the CPU is then assigned to that process which has the highest priority. That means the RAM or the ready queue is arranged or shuffled in the order of the priority of the processes. So CPU scheduler then arranges the ready queue. Now what does highest priority means? Highest priority is actually as much that integer number will be small, as much high the priority of the process will be. Now here P1 has priority 6. For example, we have another process P2 and its priority number is, for example, 2. Now P1 has arrived first and P2 has arrived second. But since this priority number is compared, so the more this number is small, the more priority of that process is higher. That means P2 will be given CPU first and P1 will have to then wait. So the ready queue gets shuffled. P1 goes at the top and P2 goes at the top and P1 comes after P2. So the more this priority number is smaller, the more the priority of that process is high. This algorithm has two flavors as well, preemptive flavor and non-preemptive flavor. But keep in mind, this is an algorithm which is generally implemented in certain circumstances. It is not commonly implemented. Only when operating system has no other option to implement a proper or more suitable scheduling algorithm, only then this algorithm is then selected. So its preemptive version is that, for example, P1 is executing on CPU and then arrives P2. P1 is executing and during its execution P2 arrives in RAM. Now the priority of both the processes are then compared. Since P1 has less priority as compared to P2, so the running process will be preempted and CPU will be assigned to P2. This is the preemptive flavor of priority scheduling. And similarly, the non-preemptive version, here whatever process comes first, no matter what priority number is associated with it, once CPU is assigned to it, it cannot be then preemptive. While other processes which are coming later on, they are then arranged in the RAM on the basis of their priority numbers. So in this case, first process will have to go on completion no matter whatever its priority is, no matter what is the size of its CPU cycle, but the other processes which are coming after first one are then organized or rearranged in RAM on the basis of their priority number. Now, shortest job first, as we discussed earlier in the previous lecture, is a type of priority scheduling in which the priority is actually given to the short processes. So it's both versions, the preemptive version of shortest job first and the non-preemptive version of shortest job first. Both are a type of priority scheduling. In the non-preemptive version, priority is given to the short processes after first process is assigned CPU. The remaining of the processes are then arranged on the basis of their CPU cycles, as we had already done in previous example. While its preemptive version, which is known as the shortest remaining time next, in which we generally see the next CPU burst time, the remaining CPU burst time of the processes. So once CPU is assigned to a process and a new process comes whose CPU cycle is then compared with the remaining time of the currently executing process. If the currently executing process remaining CPU time is smaller than the newly arrived process CPU time, then the running process is not preempted. Otherwise, the running process is preempted and CPU is assigned to the newly arrived process. But this algorithm has a problem. That's why it is very rarely implemented. And the problem is starvation. Starvation, as we had already had a discussion on this term starvation in class, every process requires a CPU. CPU is like a source of energy for your processes. Unless they get executed on CPU, their results will not be shown to you. So the process need to be given CPU at their required timings, unless they will get starved. So starvation is a common problem as CPU serves as food or energy for the processes. So how starvation can occur? Low priority processes may never execute. That means a process whose priority number is too large. That means those processes will never get a chance to be executed on CPU. New processes are coming whose priority number will be smaller than those already residing in RAM. So new processes will be taking chance to get executed, but already processes in RAM whose priority number is higher will keep on waiting, and it may happen that they would never get a chance to get executed. So this is the problem which is known as starvation. So those waiting processes in RAM will get starved. They will never get the chance to get CPU or to get execution. So the solution is then given to it. The solution is aging. What is aging? Aging is, as the name states, the more CPU cycle is getting completed, the more number is getting reduced. For example, we get aged every year. 1 year is added in our age every year. So we are getting aged. The process of aging is happening with us. Similarly, same aging mechanism will be applied on processes. But here, the priority number which is assigned with every process, one number is reduced in every CPU cycle. 1 year is added in our age and we get aged. But here in this case, one number is reduced in order to make them of high priority. So how aging works: as time progresses, increases the priority of the process. That means, for example, if a process has priority number 6 and other processes who are coming in RAM are higher in priority than this process. Some are having priority number 2, 3, 4, 5, 1. That means this process will never get a chance to execute. So what happens when a process assigned to CPU, so after every assignment, one number is reduced in its priority. So one process goes to CPU, its priority then becomes 1 is reduced from its overall priority number, so its priority becomes 5. When second process goes to execution, then again another number is reduced from its priority. Now its priority becomes 4, and this priority is then compared with rest of the process in RAM in order to see if this process is eligible to be executed next on CPU. So this is how aging, ultimately this process will become a more important process, and as its priority number will be the shortest among all the processes in RAM, and ultimately it will get a chance to be executed on CPU. So the starvation problem is solved through aging. The next algorithm is highest response ratio next. The response rate, which was the criteria we had discussed in previous lectures, the time when a process has been submitted to CPU and in what time the CPU generates first response is known as the response time. This is also very rarely used algorithm. What is it? Highest response ratio and next. Response ratio is calculated with this formula. W plus S divided by S. What is W? Is actually wait time, a process waiting in RAM or ready queue. The time a process has been waiting in ready queue as it is waiting for the processor, and S is the total expected service time. That means total CPU time. Since this is expectation, this is sort of prediction, so no process is 100% sure how much time accurately it would require on CPU. It is generally estimated time. So the ready queue is normally organized in response ratio form. This formula is calculated for every process, and then ready queue is organized on the basis of this response ratio value. The smaller the response ratio is, the higher the priority of that particular process will be. So if response rate of some process is low, that means this process will generate quick response when it is submitted to CPU. So its priority is high, it will be located at the top of the ready queue. This is a technique to prevent starvation. Instead of assigning special priority number and then applying aging, which is a quite lengthy process. So this technique is quite optimal as compared to the previous one, priority scheduling, in which we were assigning the priority number. And every process gets a chance to get executed on the basis of its response ratio. So response ratio is calculated for every process. This cannot prevent starvation completely. Starvation will happen to some extent, but far less than the priority algorithm. Again, this algorithm favors the short job. That means it is again giving priority to those processes whose CPU cycle is short. So shortest job first is again an element of this algorithm as well. But still, as I just said, total CPU time is a predicted time. It is not an accurate time. So still the service time or the execution time of the process need to be estimated. It is not accurate 100%, or it is just a predicted time. So on the basis of that, this higher response ratio is calculated, which can be correct, which may not be correct. So this is a rarely used algorithm, but is a better option as compared to the priority scheduling, where a long process of starvation and aging is generally done in order to make a process able to get a chance to execute. The next very common algorithm is round-robin algorithm. Round-robin is the most commonly implemented algorithm in our systems. Round-robin states that every process should be treated equally. No matter if a process is long or short, no matter if it arrives early or late, it should be given equal treatments. So that is why in round robin generally a time quantum or time slice is assigned to all the processes. And this is the factor in which, if you have observed in chapter 2, in previous chapter in processes, where we had discussed a two-state transition diagram in which a process from a ready state is dispatched to running, and it then from running goes back to ready. And there I had mentioned the event due to which event it is going back from running to ready. It was its time expired event. So this is the time which was assigned to that process, and if that time, that time quantum has been expired, so that process goes back from running to ready state. So that particular event depicted in two-state model transition is due to this round robin process, round robin algorithm, sorry. So here every process gets a small unit of CPU time, which we generally call as time quantum. The time quantum is within the range of 10 to 100 milliseconds. Why between 10 to 100 milliseconds? Because if we keep the quantum too large, it will become first come, first served. Again, a convoy effect will be generated if we keep the quantum larger than 100 milliseconds. So again, first come, first served will be observed. But if we keep the quantum less than 10 milliseconds, so most of the time CPU will be busy in context switching, and processor will observe the dispatch latency. CPU will be idle mode and context switch will happen. And we had discussed, when we were discussing the scheduling criteria, CPU utilization should be as much maximum as possible. So if quantum is smaller than 10 milliseconds, that means CPU will remain idle, and most of the time context switch will happen. One process is coming, another process is going out of the CPU. So context switch is happening more, CPU is idle, and more fruitful work is not being done. This is depicted in the diagram in the coming slide, which I will be discussing more the performance of this algorithm. If Q becomes large, how it becomes first come, first served, and if it becomes small, how context switch will happen more. So the time quantum has been assigned to every process, no matter the process small or the large. After the time has elapsed, the process is then preempted. It is only the preempted algorithm. It has no non-preemptive version. This is only a preempted form of CPU scheduling algorithm. So once the time quantum expires for a process, that process is preempted and added to the tail of the ready queue. So this is similar to the diagram for two-state transition model. You can revisit that diagram and see where I had mentioned a process from running state goes back to the running state only when its time quantum gets expired. Now let's observe this algorithm round robin with example. For example, the time quantum is given 20 milliseconds for all the processes. No matter the process small or large, time quantum has been set at 20 milliseconds. As we just said, time quantum must be between 10 to 100 milliseconds. So there are 4 processes in RAM here. You can see P1, P2, P3 and P4, 4 processes, and their burst time, their CPU time is also mentioned in front. But no process will be given complete CPU time at once. Instead, they will be given 20 milliseconds once, then it is preempted, then again 20 milliseconds, and in so on. It will complete its execution, or it will complete its CPU time in breaks. Now let's draw the Gantt chart. Here you can see the first process P1, CPU time starts from 0. First process P1 has been assigned, its CPU time is 53, but CPU is assigned to it for just 20 milliseconds, as we had set the quantum at 20. So after 20 milliseconds, this P1 is preempted and added to the tail of the ready queue. Now the remaining time of P1 is calculated. So 53 was its total time, 20 milliseconds has already been given to it, so its remaining time becomes 33. So it will come again and require CPU for 33 milliseconds more. Now it's P2 turn. P2 requires 17 milliseconds, but the quantum is bigger than its required time. So it is given exact 20 milliseconds. It executes for only 17 milliseconds, and 3 remaining milliseconds are returned to the operating system. Operating system then adds it to the pool of CPU time. It is not divided to among other processes, or it is not added in the time quantum. It is added to the pool of CPU time. So P2 completes its execution after completing 17 milliseconds, and then P2 goes out, and then is the turn of P3. P3 requires 68 milliseconds, but it cannot go for 68 milliseconds, rather it will take only 20 milliseconds. So at 37 it was given CPU for 20 millisecond P3, and at 57 millisecond right at the time quantum of 20 millisecond, it is stopped again. Now we reduce the 20 millisecond in order to calculate its remaining time. So the remaining time becomes 48. It is now stopped, and the last process, fourth one, is P4. It is then assigned CPU at 57 milliseconds, whose CPU time is 24, exact 20 seconds, 57, 56, 57, 77 has been assigned to it exact 20 millisecond time, and it is then preempted. So 20 millisecond is reduced from its overall time, and the remaining time it requires CPU is 4 milliseconds. Now again it's turn of P1. Here you can see P1 is assigned CPU again. Now its CPU time is 33, but it is given CPU for again 20 milliseconds. 77 plus 20 is 97, and 20 millisecond is reduced from its overall time. So its remaining time is then 13 milliseconds. Then P2 has completed, finished. P3 goes for 20 milliseconds. Time is reduced, and its remaining time will be 28. So here you can see P3 is given CPU. It goes for exact 20 milliseconds and preempted again. Now it's time for P4. P4 is given 20 milliseconds, but it requires only 4 milliseconds. So it goes to completion after 4 milliseconds. Here you can see 117 plus 4, 121, and the remaining time is given back to operating system, which it adds to the pool of CPU time. Now P4 has completed. It goes out, and we have only 2 processes in RAM. P1 again requires CPU, it is given exact 20 millisecond, but it required just a 13. So P1 after 13 millisecond goes to completion. Here you can see it is stopped. P1 is finished, terminated. And we have left with just one process, P3. P3 is given. Now it is only a single process. Even with the single process, time quantum will work, and this single process will work in breaks. Here you can see P3 twice in breaks at the end of the diagram. So it is given 20 millisecond once, and the remaining time is calculated, which is 8 milliseconds. So it is preempted once. Here you can see after completing 20 millisecond, it is preempted, and then for 8 millisecond it is assigned CPU again. So even this algorithm treats a single process on quantum basis. Even there is a single process in RAM, it has to be preempted if the quantum gets expired. So this algorithm generates better turnaround time as compared to shortest job first, but better response is response time that we had discussed. This generates turnaround time is higher as compared to shortest job. Or turnaround time was the time required for a single process to complete its execution. So as compared to shortest job first, round robin can bring delays in the completion of a single process, but the response time is far better. That means response time gets reduced in round robin. So this algorithm is the most commonly implemented algorithms in every latest operating system. Turnaround time is though becoming higher, as a process requires just P1 requires 53 milliseconds, but it is getting to completion at 134 millisecond. Here you can see 53 millisecond is the time it requires, but getting completed at 134. That means turnaround time is getting affected, but the response ratio or the response time is getting reduced. Every process is getting chance to have response generated from CPU right after 20 milliseconds. Now this is the diagram in which we were discussing the performance of round robin algorithm. If the quantum becomes too small, what will be the response of this algorithm? And if the quantum becomes higher than 100 millisecond and smaller than 10 milliseconds, so what will be the response? So here you can see we have a process whose CPU time is 10 millisecond. Now we are to divide the quantum between 10 to 100 millisecond as we just said. Why? Because too larger than 100 will make it first come first served, and smaller than 10 will make the system busy in more context switch and CPU will remain idle. So now the quantum is 12. That means it is within the range of 10 and 100 millisecond. So a process whose CPU time is 10 milliseconds, so there is no context switch. It goes to completion in one smooth cycle. Here you can see, as quantum is more and its CPU time is small, so there is no context switch. It is not stopped, it is not preempted in the middle. Now we keep on reducing the quantum. Now quantum is reduced to 6, which is less than 10, which was our arranged defined range for quantum. Now here you can see the process time is 10 millisecond. After 6 quantum cycle, after 6 unit time, or after 6 millisecond, which is the quantum defined for this process is preempted once. Here you can see preempted once and then assigned CPU again for the rest of the time. So one context switch has been occurred. During context switch, a process goes back to the RAM and CPU is idle during that stage. We had discussed the context switch in detail in chapter 2 when we were discussing processes. A complete description how operating system stops CPU, saves the context of a process in its PCB and loads the context of another process from its PCB, and then CPU is assigned to another process. But in this case, only single process is there. So even a single process is preempted right when the time quantum gets expired. So it is preempted, its context is saved in its PCB, and its context is reloaded again when it is its turn to get executed again. So once here, after 6 milliseconds, this process is preempted. Now we reduce the quantum furthermore. It becomes 1. So here you can see this process requires 10 millisecond for its execution, but after every 1 millisecond it is getting preempted. Here you can see this breaks, you can see these breaks. After every 1 unit time it is getting preempted until it goes to completion. So total number of 9 context switches occur. That means a total number of 9 context switch makes a CPU to get delayed 9 times to complete the execution of a single process. So this is the reason if you reduce the quantum time from 10, so the more CPU will be remain idle. CPU utilization will reduce. So this is the reason the range has been defined between 10 to 100. If you exceed it from 100, it will become first come first serve. So large process will be favored and small process will have to wait for long in RAM. But if you reduce the quantum from 10, the CPU will be idle more, and what happen will more is the context switch. Operating system will be busy in switching the context of process, even a single process is there, and CPU will remain idle. CPU will not be able to perform any fruitful activity. So this is the performance diagram of first come first serve, but this is the most commonly implemented algorithm in almost all of the modern operating systems. That is all for now. Here we come to the end of CPU scheduling chapter. In today's discussion, we discussed remaining of the CPU scheduling algorithms, such as the priority scheduling, in which typical priority scheduling assigns a priority number, which is an integer number, to every process, and the RAM is organized on the basis of that priority number. The smaller that priority number is, the higher the priority of that process will be. It is in 2 flavors or in 2 versions, preempted and non-preempted. Both versions are available. Shortest job first is a type of priority scheduling, but this algorithm is rarely implemented due to starvation problem, and the mechanism solution applied to resolve the starvation issue is aging, which is a time-consuming and hectic process for operating system, as it has to reduce one number from the priority of every process in order to make them eligible to get a chance to be executed. The next algorithm that we discussed was the response ratio algorithm, in which response ratio is calculated on the basis of formula, and the RAM is organized on the basis of that response ratio value. The last algorithm that we discussed was the Roundrobin algorithm, which is the most optimal one and is used in almost every operating system, as it treats every process equally. It assigns a time quantum to every process, and once the time quantum has been expired, the process is preemptive. So this algorithm comes in just preemptive flavor. That is all for now. I hope the topics must be clear to you. If you still have any queries, you can email me or ask me on KCMS. I thank you all.